Hello and welcome to this video tutorial on the use of the Mann-Whitney U-test. So the Mann-Whitney U-test is one of our inferential statistical tools that we use in psychology to ascertain whether we have statistically significant data or not from a particular investigation. We have a question here. I'll go through this as we normally do. We're going to go through our alternative hypothesis, null hypothesis, etc. And then I'm going to show you how to do this. What I would say is probably one of the more difficult tests to do. Anyway, hopefully by the end of this session you'll find it quite straightforward. Are girls more friendly than boys? Okay, is our question. That's our research question. Let's see what we can put down as a hypothesis then to start off with. Okay, so remember we always start off with two hypotheses. What's that? There we go. Right, brilliant. We start off with an alternative hypothesis. This is where we think there's going to be a difference of some sort. You know, our statistical test is going to show that there is a difference here, and that girls are more friendly than boys, or boys are more friendly than girls, whichever way it is. And also we have a null hypothesis. A null hypothesis simply says that actually there might be a difference, but it won't be statistically significant. So don't worry about it. It's been caused by some sort of chance event. Okay, so our alternative hypothesis then, there will be a statistically significant difference. There will be let's put in there, shall we? A statistically significant difference between the friendliness scores of girls, measured using a rating scale, and the friendliness scores of boys. Okay, so all we're saying is there's going to be a difference between them. We're not saying in what direction it's going to go in. And there's the null hypothesis there. It's our default position again. There will not be a statistically significant difference between the friendliness scores of girls measured using a rating scale and the friendliness scores of boys, and any difference will be due to chance. So that's where we're starting from. So as we go through this statistical test, we need to keep that in mind. That's what we're trying to see, whether we've got any data to actually back that claim up, or do we have to default back to that again? Right, let's go back to the top and work this one through. Mann-Whitney U-test then. So we have friendliness scores down the left hand side here. You can see you've got column A girls scores. How's that been worked out? By some sort of questionnaire, I imagine, or some sort of observation, or whatever. But there's been a ranking given. You can't measure friendliness objectively, can you really? You know, there's no friendliness quotient that someone has that you can simply measure. It's something that someone's going to have to come up with some sort of questionnaire to determine it, I imagine, or an observation, like I say. So there's the column A scores down there. Okay, therefore the girls, and we've got column B, the scores for the boys there. All right. That's all you need to be dealing with at the moment. Just ignore the red scores, because that's going to be something I'm going to discuss in a moment. But let's just think about why this is a Mann-Whitney U-test then. One of the problems that students have is they very often mix up nominal data with ordinal data. And we've got a bit of a combination of both going on here, really, I suppose. But ordinal data is the highest level, so we're going to use that. Why have we got nominal data? Well, we've got nominal data, I suppose you could say, because we've got girls and we've got boys. Okay, you're only in one or the other, aren't you? So that is kind of nominal. But look at this: we've actually got ordinal data here when we've actually measured the DV. And the ordinal data is the ranking score, isn't it? The rating score that we've got. Why is it ordinal? Because it can be placed in some sort of order. You could say you've got people who've got very high scores, might have 25 or whatever, and then we've got people with very low scores, much lower than that. Okay, that's an order. That's a ranking, isn't it? You can't do that with nominal data. In fact, what would have happened here, if this had been nominal data, you simply would have had high scores and low scores. So if you remember the chi-squared, if you go back and have a look at chi-squared, if you haven't done so already, this would have been a 2x2 contingency table with girls score, boys score, and then high and low. That's all it would be. See that? Two different types of nominal data. This is ordinal. Hope I haven't gone on about that too much, but hopefully you understand what I mean. Right, big problem with the Mann-Whitney U-test is it's a real fiddly little devil, and that you have to do ranking again, just like you do with Spearman's rank and Wilcoxon, etc. But in this particular situation, you're going to use all of the data, all these black numbers are all going to be taken as one giant data set. Okay, so even though they do appear in two columns, they're going to be taken just as one big homogeneous blob of data. Why is that a problem? Because it can be really, really fiddly and really hard to work out whether you've made any mistakes as you're going along. So what I do with these, and I think this is quite a useful thing, particularly if you've got lots of data here, is to actually create a ranking table. All you need to do with your ranking table is just put your scores, so just find out what scores you have. So I've just gone through that and I've worked out that you have scores of 2, 3, 4, 5, 6, 7, 8, 9 and 10. So no one got a friendliness score of less than 2, in other words, which is good to hear. And then what we do there is we put our ranks. Okay, so what ranks are we going to use? And then we have our final rank. So this is kind of like our adding up stage and dividing stage or what have you. And this is our the final rank that we're going to give to each one of these scores in the table. Right, let's work this one out then. So I've said here that the score 2 has got a rank of 1 and a final rank of 1. Why have I said that? Well, the reason is because there's only 1 2 in that table. Okay, you can see there's a 2 there in that column. Is there a 2 there? No, just the 1. Okay, that means fortunately we can start off with a rank of 1 there. That's the only one we've used. Now remember, with ranking we go from the smallest to the largest. So the smallest number, the smallest rating that we have in this particular situation is going to get a rank of 1. Okay. That's the easy bit. Now it's going to start to get a little bit more tough, okay? Because the next score was 3, right? Well, there's 3, and there's another 3. There's no 3s over there, but we've got 2 3s here. That means we've got ranks of 2 and 3 that have to be used there, because we've got 3 sets of data. We have to use all of the ranks, okay? So 2 and 3, we can't put that next to it. So what we do is we do a little bit of jiggery pokery here, where 2 plus 3 equals 5, divided by 2 because there's 2 of them, 2.5. So that means that each one of those 3s gets a rank of 2.5. I'll do a bit of a tougher one here, shall I? Okay, so as we work our way through, the score of 5 appears 1, 2, 3, 4, 5 times. Okay, so let's just see what we mean. Well, there's 1, and there's 1. And there's 1, and there's 1, and there's 1. Okay. Now, by the time we've got there, we've already used ranks 4 and 5. So the next ones we're going to be using are 6. Yeah. And we have to use 7 and 8 and 9 and 10. What we do is we add them all up together. Okay. And we divide them by how many there were, divided by 5. And that means we get a ranking of 8 for each one of those. Okay. Do it yourself. You can make sure you understand what it is we're doing. Anyway, we work through the rest of the table in just the same way. You can see my ranking table there. And hopefully we get our ranks correct. Okay, that's a very, very important we do. If we don't, we are snookered. All right then, what do we do now then? We have 2 columns. Let's go back to this big table up here. We have 2 columns, rank R1 and rank R2. All we're going to do is we're going to add them up separately now. So that's the last stage of us dealing with the data as one big data set. We're going to add them up separately. And R1, if you add all those up, equals 178.5, and R2 equals 121.5. Now remember that number there, because that's very important. All right, let's go down and see what we're going to do now. Remember, we've already been through our alternative hypothesis and null hypothesis, so we know where we are. What we're going to do with all this information, we are going to plug it in to this lovely little formula here. Remember, you don't need to know the formulas, you just need to know how to use them. You'll be given those in an exam should you have the misfortune of having a Mann Whitney question to do. All right, so do you remember which one was the smallest? Yeah, it was the row 2, okay, R2. It was 121.5, wasn't it? So this is the one we're going to use. We're going to ignore that. We're going to use this one, okay? Right, so we just simply plug it into the equation, and so R2 was 121.5, and then it's going to be minus. Now, N2 is the number of data points in that particular column. Trust me, you can go back and have a look if you want, but there was 14 of them altogether, all right? So 14, and then 14 again, minus 1, so that's 14 so that's plus 1, sorry, that should be a plus, I do apologise. 14 plus 1, 15, so 14 times 15 divided by 2 equals 16.5 when you do that. Let's just change that to a plus whilst we're about it. There you go. Lovely. Okay then, right, so we've got U is 16.5. Now, you should know that that's not the end of it, because we need to work out whether we can support our alternative hypothesis or not. How are we going to do that? By applying our information to this wonderful thing here. And this is an example of a Mann Whitney U test critical value table. Now then, we have two different, we have obviously a row there, we have a column here, we have N1 and we have N2. What do these relate to? Well, it's the number of participants in each one of those columns. Now, if you look back up at the table again, you will find out that there was less females than there was males. Okay, so N1, which we're going to say is females here, was actually 10. All right, so there's 10. N2, which was the males, which was 14. Okay, so there's 14. So just in the same way, we just cross-reference, there you go. And 36 is going to be our critical value. Right, is it significant or not? Well, in this particular case, why is that not moving? Right, okay. In this particular case, the calculated value of U must be equal to or less than the critical value for significance to be shown. 16.5 compared to 36, well, 16.5 is less than 36. Hooray, we've actually got something which is significant for a change. Can you accept the alternative hypothesis? Yes, because it's smaller, as the observed value is less than the critical value. And there's our significance statement. Right, significance statement, U equals 16.5. We have to put the two figures for N in this particular case. N1 equals 10 and N2 equals 14. P equals less than 0.05. Yes, we can accept our alternative hypothesis. There is a difference in the friendliness scores of girls and boys. Maybe girls are more friendly than boys, or boys are more friendly than girls. We can't say that, but all we can say is that there definitely is a statistically significant difference. Okay, hope that was useful to you. Do go through that as often as you want to, because it's not the easiest ones. Okay, many thanks.